Thank you for the introduction and welcome everyone. Today we want to talk about the system management mode and malware inside the system management mode. This topic has been researched for at least 10 years now, and there are several concepts. We'll talk about these previous concepts and would like to bring it to, so to say, to a new level with some advanced concepts that can help to get a better understanding for the threats of the system management mode and malware inside. Just as a short introduction, my name is Sebastian Schrittwieser and I'm a lecturer for information security at the St. Pölten University of Applied Sciences. And we also have a research center at the university, and I'm heading the center Target. As the name already suggests, it's a research center that researches the threat of targeted attacks against IT infrastructures. And our work in this system management mode malware was also part of this center because we had the problem that we wanted to analyze targeted attacks and didn't have the attack tools to analyze these attacks and to see what the consequences are of these tools. So we had to develop our own. And my colleague Julian Rauchberger is student at St. Pölten University of Applied Sciences in the master course of program in IT security, information security, and is also a research assistant at our Institute of IT Security Research at the university. As a short agenda for today's talk, I would like to first start with some background on what the system management mode is exactly, what it is used for, why it is still there, and what the good aspects, so to say, are of the system management mode. Then I would like to give a short overview on previous works on system management mode malware and what was done before. And then I would like to discuss the limitations of existing approaches and what the problems were that we had during our research on targeted attacks. And then Julian will continue with introducing our advanced concepts for SMM malware. So we would like to give a short introduction in writing SMM code. I don't know if someone of you has done this before. And then we'll talk about our advanced concepts. So we talk about 64-bit support for SMM malware. So how to go into the long mode and use the entire range of 64 bits. And then we'll talk about operating system awareness, so that from the system management mode, we have a deeper understanding of the operating system that runs, and the interaction with the operating system is then possible in a much fine, granular mode. And we'll also talk about stealth features. So system management mode and malware inside is per se stealth, or more stealthy than malware in the operating system, but still there are pretty obvious ways of detecting malware in the SMM, and we will discuss some stealth features to make it more difficult to detect them. So I would now like to start with the system management mode and a short overview on the system management mode. So the general concept is it's an operating mode in x86 CPUs, and it's quite old. So it was first introduced in the late 80s, and the original idea was to use it as a maintenance mode inside the CPU for example, power management or thermal management. And nowadays there are lots of additional functionalities that were added to the system management mode by vendors. So for example, the original idea was if some part of the hardware, for example, gets too hot, then the CPU can switch to the system management mode and then do something to protect the hardware from damage. And nowadays there are other things like USB legacy support or forward calls to a trusted platform module. That's things that vendors added to the system management mode during the last 25 years. And the interesting thing about the system management mode is that it suspends the operating system that was running on the computer and then executes the system management mode with very high privileges. So there's free access to the memory. You can interact with the memory in any way you want. There are no hardware protections enabled, and this gives you, of course, a lot of power from this mode for the interaction with the operating system. Inside it, it's quite similar to the real mode, so again there is memory segmentation, and you can address it with a segment selector and an offset. Yeah, and an overview, it looks like this. So the operating system is running on the computer, and then there is a system management interrupt, the SMI, and at the point of an SMI, there is a complete context switch of the CPU into the system management mode. So first the context is saved, and then the system management mode is executed. After that, you can return then with a context restore, and then you go back to the operating system. It continues with the execution as nothing happened. For this system management interrupt, as I said before, it's a complete switch, so it switches to the mode, and then afterwards it continues where the operating system paused. And when an SMI is called, then all processes and all cores are placed into this mode. So it's something that's not possible that only, for example, one core goes into the SMM, then does something, and then switches back while the operating system is running on another core. There was an attack on this, or there's a race condition that was shown before a few years ago. I will talk about this later. All the processes and cores go into the system management mode, or should go into the system management mode at the exact same time, but still there are some differences, and it was possible to attack the SMM with race conditions. And the SMI has the highest priority interrupts in the CPU. Of course, this makes sense, because if something with the hardware is wrong and you don't want to break the hardware, then it should go into the SMM, of course, immediately, do whatever it needs to do to prevent damage, and then go back. Restoring, as I said before, context save is done automatically when you go into the system management mode, then you restore it with the resume instruction. Then you go back to the operating system. How to go into the SMM, so how to invoke this SMI. So you can do it in software. That's like we do it for our malware concepts in the SMI and the SMM. So for software-initiated SMIs, you have to do an I/O access to a specific port. There is one very common port, but this can change from vendor to vendor. And other possibility would be for the hardware to signal to some special pin on the CPU. For example, you have some thermal sensor, and if something gets too hot, then there is power on the specific sensor, which then means that this SMI is invoked, and we go to the system management mode. And there's also the possibility of the firmware to request that the CPU goes into the SMM when there is a I/O write on a specific location that the firmware defines. Inside the system management mode, it's a very separated mode from everything else. So the SMM code that's executed is only visible to the CPU in the SMM context. And there's also the SM RAM, and inside the SMMs there's read-write access from the SMM code to this SMRAM, but from outside, this SMRAM is not visible, so it's only inside. It's a complete separated environment. Additionally, interrupts are masked, so it's not possible to kick you out of the SMM. Of course, this also makes sense. If something with the hardware is like too hot, then you don't want that something else can kick you out of the SMM before you can repair it. And there's also inside no paging, so the linear addresses are the physical addresses. So as an overview, it looks like this. We have the system management mode that runs in a complete different context. But from the system management mode, you can go inside the memory, change the operating system's behavior, because you can read and write the system's memory, but not in the other direction. So for system management mode malware, the thing is, they have very high, or malware in the system management mode has very high persistence, because it's completely independent from the operating system. So it means if you do a clean install of the operating system, malware that is inside the BIOS or the UEFI is still there, and you can't remove it by just reinstalling the operating system, because it's a separate location. It has very, very high privileges and high stealth, because it's not in the operating system. For example, an antivirus scanner can't see it because it's in some other separate location. So for SMM malware, there are different infection stages. So the first one is you have to get to the SMRAM somehow. This can be done by some exploit, or going directly through the hardware, or through some BIOS update, or something else. Then usually you have to bootstrap your SMM malware inside there. So for example, it has to find itself in the memory. We'll talk about this later on with the advanced concepts. Then it has to be invoked through an SMI from the operating system, and then it has to maintain its stealth inside there, because of course there is interaction with the SMM and the operating system, so there are some traces, and we'll also talk about stealth features to prevent an analyst or software from the operating system to detect the modifications of the SMM malware. And then, the payload is executed as interaction with the operating system through memory access to the operating system's memory. About 10 years ago, the first concepts for SMM malware were introduced, and there are very different research areas in this. So for example, there was research on general weaknesses of the SMM. So it's quite obvious that security has been an afterthought in the specifications of the SMM in the late 80s, and you can see it everywhere, that there are general weaknesses of the SMM that make it easier to do malicious things inside the BIOS. Another problem are the UEFI variables. So these variables are readable or accessible and writable from the operating system, and it was, for example, shown that it's possible to do memory corruption through UEFI updates because of this problem. And there are also the boot scripts. They make startup faster during suspend and resume operations, and often they are not stored in a secure way, and it's also possible to modify them and then modify the behavior of the entire system. And there are also some very specific attacks. For example, there was the concept of the speed racer. That was something I mentioned before, with the race condition, when not all the cores of the CPU switch to the SMM at the exact same time. There was also the concept of a memory sinkhole. This allowed the attacker to sinkhole a small range of the SMRAM and then hijack the execution flow. And there was also a cache poisoning attack. It was the idea that some parts of the SMRAM were flagged as cacheable, and when they were cacheable or flagged as cacheable, then they were writable from the CPU, from the operating system, and then the context switch to the SMM mode, system management mode, then brought back the cacheable version to the SMM, so it was possible to write the SMRAM or a cached version of it outside of the SMM mode. And there were also some practical examples. So, for example, in 2015, it was shown that, or there was a concept where there was a userland process, and it was able to signal to the rootkit in the SMM mode that it wanted to be elevated by writing some magic number to a specific register, and during the next system management mode interrupt, the rootkit detected this magic number and then granted the process root privileges. There was the watcher. Watcher was quite a similar concept, so it was able to scan the memory for specific signatures, and if a signature was found, then for example, this process then was again elevated. Also, the NSA has its own SMM rootkits. They call it the implants, and then there was another concept, the light eater, that was more or less the most advanced SMM rootkit we have seen so far. The idea was, or the text scenario was, that you infected Windows users that sometimes booted Tails, and it found PGP keys inside the memory, and also decrypted emails of the class email agent that was part of Tails. And this rootkit was even able to get this data then out of the system through networking, and it wasn't even possible or necessary to write the own network drivers, because it was possible to use a serial over LAN and then get the data out. But what we see, or what problems we had with all these concepts were, they were all for very specific use cases. And often the interaction with the operating system was done through quite inefficient search patterns. So, for example, the watcher just searched for one specific pattern. If it was found, then this process then was elevated, but nothing more. Then all of them are 30-bit only, so only the first 4 gigabytes of memory are accessible. So no complete interaction with the operating system is possible, and the stealth, of course, is also quite limited. So we saw that all these concepts we had before were quite of limited use for our research and for the research community as a whole, and it's quite difficult to conduct follow-up research on these previous approaches. And yeah, we also have seen quite slow research progress in this area in the past 5 years. And that's something we would like to change, and would now like to introduce some advanced concepts that we also would like to then share with the research community when we're done. I will talk about this at the end of the talk, but now I would like to give the mic to Julian, who will introduce the advanced concepts we implemented in our center.
Thank you very much, Sebastian. So when we started with implementing our rootkits, we checked which rootkits are available to researchers. So what can they use, what do they use if they want to test the detection technologies? And there really are a few available. Some are kernel level, some are userland, but there is no system management mode rootkit for researchers which they can use to test. And we thought that's actually quite a pity, because it's a really interesting concept. It's one of the very few instances where the malicious code runs with a lot higher privileges than the code that tries to detect it. So that's a really cool challenge to face. So I'd like to start out with how actually can you develop code for system management mode, because I thought this info is a bit lacking on the internet. You get some info about how it works, but I'll give you the details, how to set up a development environment, and how to get your code up and running in there, and how the memory layout looks like. So if you're interested, please have a try at it. First, you'll have to decide, how do I want to get my code into system management mode? How do I want to load it? And you pretty much have two possibilities. The first one would be an exploit. If you have an old system older than 2006, chances are really, really good that those protection techniques simply aren't there. So you can just load your code into system management mode, because in old BIOSes, vendors often simply didn't use any kind of protection technologies. But nowadays, this is getting harder and harder, especially if you consider stuff like signed code. Those exploits are still there, and if you're a state actor or something like that, you'll surely find one. But for development, it's not really optimal. So the second method, which is the one we used, is during boot. And we implemented a custom version of the open source CBIOS that loads our rootkit during an early phase in boot where the system management RAM is still not locked. And yeah, that works really well and is also not that hard to implement. And when you want to test your stuff, real hardware would be great, but it's extremely cumbersome to develop for it, because every time you want to test your code, you'd have to reflash the BIOS, and that's really not that comfortable. So we decided to use virtualization, and you'll have to use specific hypervisor versions which work well with system management mode. Some others don't work that well. QEMO, starting from version 2.5.0, works really well if you run it on a Linux host system with at least kernel 4.4 and also kernel virtualization extensions enabled. And of course, you'll also need hardware virtualization support in your CPU, but that's not really an issue because pretty much every new CPU has that. So, how do you want to write your code? We started out in C, but that wasn't really a great idea because you'll need access to lots of uncommon instructions, and those simply aren't part of C. So our code ended up being 3/4 inline assembly, and that was plain ugly. So we decided to re-implement everything in pure assembly. You have better control over addressing. In my opinion, it's one of the instances where assembly works really well and where it's easier to use than C code. And yeah, for generating the SMIs, for testing, you can write to the advanced power management control registers. There is a specific port which depends on the hardware, but you can Google it for your system. You simply write to that port and the system management interrupt is generated. Very, very handy for testing. Okay, Sebastian explained that when a system management interrupt occurs, that the CPU enters system management mode. What actually happens is that the CPU stores all the registers in the state safe area in SMRAM and then changes 2 of those. It sets the code segment register to the value of the SM base register. That's configurable and it contains the start of the SMRAM. Per default at reset, that's hex 30,000, but that depends on the UEFI implementation where it's actually located. But the code segment gets overridden with that, and then the instruction pointer gets set to hex 8000. So if you want to run your code into system management mode, you'll have to write it to the offset 8000 after the start of SMRAM. And really we have a small graph of the layout. The first area between 0 and 8000 is actually unused, it's undefined. We found that often stack is put there, but you can do whatever you want. Then at 8000 the actual code starts, and at the end at SM place plus FE00 there is the state safe area where all the registers get stored. And what you can actually do is you can change them. You can write to the state safe area, and when the operation returns to the operating system, those values will be restored. So you can actually influence the values of those registers there. Okay, Now taking all that into account, that the system management RAM is really changes depending on the system where it's located, we thought that it would be most useful if we write the whole rootkit in position-independent code. That's actually not much of an issue because the code segment gets set to the start of SMRAM. So we can just read the code segment and know where the SMRAM starts, and then we set up a stack. Because, like I said, the stack registers don't get changed on SMIs. So if we just use instructions that use the stack, we'd use the one the operating system used, and of course, this might break stuff, so we don't want to do that. We set our own stack up by setting the stack segment pointer to the same value as the code segment. So it's at the very start of SMRAM. We'll also need to set the stack pointer to a small value like 2 or 4, so we have a bit of space there. And then we'll use the old shellcode trick by calling a function and then using pop to get the instruction pointer that's pushed on the stack. So, old trick. But you can then use that to calculate the base of the SMRAM and address all your functions and structures relatively to that. So, okay, now that we know how to get our code into SMRAM and know how to find ourselves, the next question is, what do we do with the operating system? How do we interact with it, and how do we root it? Well, the first issue we face is that we can only address 32 bits of memory per default. Because, like Sebastian said, in SMRAM, the code is kind of similar to real mode. It's actually old school 16-bit code. So you can only address stuff by using the segment registers. And this has a limit of 32 bits. But most newer systems will probably have more than 4 gigabytes of RAM. And a complete rootkit should be able to access all of that. And the solution we came up with for this is that we put the CPU back into long mode. So we actually do the same thing that the kernel does when booting up, that puts the CPU into the 64-bit mode so we can execute 64-bit code while still staying in system management mode. So that is actually possible. And even though it's not documented by Intel, you can directly switch from real mode to long mode, skipping protected mode, which works very well for us, and we've also read a few papers that say it worked for them as well. So that's cool. The first thing we have to do when we want to set up 64-bit support is configure page tables, because in long mode that's mandatory. They don't have to be fancy or anything like that, they just have to be there because it's mandatory. The same is with the global descriptor table. We'll also have to set one up, and then we'll set a few flags and enable a few features, and the last step is to update the code segment, but I'll get to that in a minute. So first, configuring page tables. We use simple identity mapping, which means we map the same physical addresses to the same virtual addresses. For our use case, that works quite well. And the structure we have to set up in memory looks kind of like this. You have a page map level 4 table, which points to page directory pointers, which in turn point to page directories, which then point to the real pages. Now, we could use 4 kilobyte pages, 2 megabyte pages, or even 1 gigabyte pages, but the 1 gigabyte ones aren't supported by every CPU, so we decided to use the 2 megabyte pages because support for that is a lot older. And the way it works is you have one page directory pointer per each gigabyte that you want to be able to page. So to that graph, you'd have to add a second page directory pointer, which in turn points to page directories if you'd want to map a second gigabyte of RAM, for instance. And once you've set up that in memory, you tell the CPU that you want to use it by loading the physical address of the page map level 4 into the CR3 register. And that's pretty much everything you have to set up there. We'll actually enable that one then later. But one thing I'd like to point out is that you have to set some flags for every entry. The first one is the present flag, so the CPU actually knows that these are paged in and not swapped out on the disk. And you should also set the read-write flag so it's accessible by us. Okay, the second step is the global descriptor table. Again, a bare minimum one is sufficient for our use case. The global descriptor table is used for segmentation of the memory, but in 64-bit mode it's more of a legacy kind of thing. It only has 3 descriptors in our case. The first one is a null descriptor. That one is easy. It's just there because it's required by the architecture. It has every bit set to null. The second one is a code segment. Important here is that we set the bits so it's marked for 64 bits because we want to run 64-bit code in this segment, so it has to be marked for that. Regarding the size, you can just let it span the entirety of RAM. It doesn't really matter in that case. And then we'll have a data segment, which is readable and writable, of course. And that's pretty much the same like the code segment. It just has the read-writable flags instead of the executables. And then, when we have set that up in memory, we use the load global descriptor table LGDT assembly instruction that again tells the CPU to use this specific global descriptor table. And after that, we'll need to enable some features. The first of those is the physical address extension bit in the CR4 register, then the long mode enable bit in the extended feature enable register, and we'll also need to enable protected mode because that's just required by the specification, and paging, which are located in the CR0 register. So these are just simple bits which you flip to 1, and then long mode is enabled. But actually, it still only runs 32-bit legacy code because what we additionally need to do is update the code segment register to use the code segment we defined in the global descriptor table. And unfortunately, you can't simply write to the code segment register because that doesn't work like this. We'll need to do a far jump into the code segment. This pretty much works like a normal jump. You specify the address you want to jump to, but you also specify the offset of the entry in the global descriptor table which you want to use for that jump. So we specify the offset of the code segment, and then the code segment register gets loaded with that, and the CPU knows, okay, this section contains 64-bit code, and switches to real long mode. And what this allows us to do is now run real 64-bit code inside system management mode. So we can take advantage of all the advantages of long mode. For instance, we can use instruction pointer relative addressing now, which makes writing position independent code a lot easier. And we can also access the full 64 bits of the registers of the CPU, which is also quite handy. Okay. Now that we are running 64-bit code, the next question is, how do we interact with the operating system? Because even though we set up paging, we still can only directly address physical addresses. And the operating system, of course, uses virtual addresses, so we'll kind of have to translate here. Now, what we could have done is we could have actually used the page tables of the operating system, but that's not that great because it's not guaranteed that our own code is mapped where we want it, and we also don't want to modify the page tables of the operating system because that wouldn't be that stealthy and might cause some problems with it. So here again, our solution is we just simply pass the page tables the operating system used and do manual translation between virtual and physical addresses. And this kind of works like that. I explained the structure of the page tables before, but it's kind of the same here. We have the CR3 register, which is stored in the state safe area, so we just read it from there, and that's the physical address of the first page table level. And we take the virtual address we want to translate and split it into multiple parts. And then we use the first part, in this case the level 3 index, And that's the index into the first table we located. So, for instance, if that's 3, then we use the third entry from this table. And this will again point to the next level of the page tables, where we have the next, where we use the next index to again get the next pointer, and so on and so forth. And the last one then points to the physical page where the data is actually contained. And we add the physical offset to that, and we have successfully translated the address to a physical one. And now this one we can access from SMM. So what this allows us to do is translate every virtual address used by the operating system, for instance, kernel symbols, to physical address and then access it. And this really gives us a lot of power over the operating system, because now we can, for instance, locate the interrupt descriptor table and overwrite whatever we want in there. Now, the real question is, how do we intercept functions? How do we hook that? Because, like we said, we want to have this available for researchers, and when they test their rootkits, they want to be able to compare it to traditional kernel-level rootkits. So one of the goals we really had with this was to implement traditional features like monitoring syscalls or stuff like that. And yes, in order to hook those functions, we use the hardware breakpoints. Now, it's a bit difficult to do this in a really stealthy way, but I'll come to that in a bit. Pretty much what we do is we use the hardware breakpoint to configure, for instance, a breakpoint if the kernel executes a syscall. And when this interrupt gets called, when the debug exception occurs, it will generate interrupt with the number 1. And what the CPU does then is it looks into the interrupt descriptor table and gets the address of the function there, and which is supposed to handle that, and executes that. What we do is we want to map this into system management mode, so our rootkit gets executed when the function is called. So we simply overwrite it. Now, this doesn't sound that stealthy, but I'll get to that in a minute. We overwrite it with some assembly code, which simply writes to the advanced power management control registers in order to generate a system management interrupt. So what this does is, whenever a hardware breakpoint is hit, our rootkit gets executed. Now, how do we achieve stealth with that? The issue is that we just overwrote some kernel memory, which of course could be detected. But this handler which we installed also is only 8 bytes long. So we can create a read-write breakpoint over those 8 bytes of memory. And whenever the operating system tries to read that memory to see if it has changed, hardware debugging exception will be executed first. So our rootkit gets called whenever the operating system tries to check that piece of memory for modifications. And now the last thing that's left is, what is if the operating system directly tries to read the hardware debugging registers to see if something has changed there? Well, luckily Intel provides a feature which is called the general detect flag. And if we set that flag, the CPU will actually generate a debug exception whenever someone tries to access that register. So again, when the operating system tries to read those modified registers, debugging exception occurs and our rootkit is executed before. So we get notified on all those occasions where the operating system tries to detect the rootkit. And what we can do then is we could fake the result of this read, or we can simply just delete ourselves from SMM and make it really, really hard for those forensic guys. And well, we have actually a working implementation of all that which I talked about now, and Sebastian is going to give you the details.
Yeah, we called this system LongKit because it works in long mode. And our idea was to have a universal framework for SMM malware that can be used for research. Right now it's about 1,000 lines of position-independent assembly code. And yeah, we'll make it open source and give it to the research community. We're still discussing how we prevent this being used in a malicious context, so not giving it to everyone, but just to known whiteheads when they approach us. But we're still in discussion and would like to release it in the first quarter of 2017. So if you're interested, just drop us an email and we'll get in touch with you when it's ready for release. The basic features of LongKit will be everything we discussed in our talk. So it has full long mode support for 64-bit CPUs, and it's completely operating system aware by parsing the page table used by the operating system. It's easy portable to other systems. We use position-independent code, so no matter how the implementation of the actual BIOS WAF is, it will be possible to get it running there with minimal modifications. And we also implemented two typical rootkit functionalities, so login bypass and system call hooking. That's something that is already done, and it's quite modular, so extensions with other functionalities for research scenarios will be possible. Yeah, so to conclude this, in our research we found out that the threats from SMM malware are even bigger than previous research has been shown, because the interaction with the operating system is possible in a very controlled way by getting knowledge of the entire structure of the memory and so on. And yeah, this OS awareness was something we had in mind when we began with this research, and yeah, it's very possible to do so, and very targeted interaction with the operating system is possible. And as a final remark, as I said before, there will be an open source release of this LongKit to, on the one hand, encourage future research into this SMM malware, and it will be useful for other BIOS and WAF research as well. So we found several incomplete implementations in this area, for example in the CBIOS, and we think that our code will also help to make this, for example, this CBIOS implementation more complete in the future. Okay, thank you for your introduction, and if there are any questions, we're very happy to answer them.
So, are there any questions? None? Too early, too less coffee for the people.
Sorry for the question. Okay. So defense, how much work or thought have you put into defending initial infections? Let's say via rootkits.
Well, okay. In my opinion, the best way to defend against these BIOS-based rootkits is actually not getting infected at all. And okay. Now this sounds hard, but Intel has actually put a lot of effort lately into providing signed code for the BIOS. So it's really possible to have a system where the BIOS can't be just reflashed with something else. You'd need a valid signing key, and Intel has implemented this directly into the CPU that you can check the signature of the BIOS, and if some malicious guy modifies it, then then it won't boot. The way around this would be if you're really a state actor or something like that, you could probably get the signing key from somewhere or get it signed. So that's an issue. But yeah, once it's running, it's really complicated. You might be able to do some timing-based stuff and see if for instance, those syscalls take a long time, because of course there's overhead involved with switching to system management mode. But yeah, well, we really hope to inspire some research in this area, because there isn't that much really.
I remember some ideas by Xenokova on actually using rootkits to detect rootkit infections. So because you're on that deep level, basically, so I don't know, that's maybe an idea.
Yeah, that sounds really interesting. But you know, if you get access to SMM, you might be able to wipe that rootkit which is already there. So, but it's really cool. I think that could work really well.
At least you bring the defense to the same level. Right now we have the problem that the rootkit is on a much higher level than the defense mechanisms, and by using a rootkit to detect a rootkit, yeah, we have the same level at least.
So, are there further questions? No? Then how do we get it, the long kit? Just drop you an email or?
Yeah, just if you want to get access to it, just drop us an email and we'll notify you when we're done with everything and can release it.
Okay. So, more questions?
Another thought about using that as a way to stealthily instrument and track system calls in a sandbox. So basically like an OBIS, but on that level. Maybe that's an idea for the future.
That will of course also be possible, and I've also thought about testing it and using it for that, but we didn't really have time for that yet. So, but it's of course it could also be used for good purposes. You are running over the kernel, so if there's another rootkit in the kernel, you might be able to find that from there really well. But yeah, it's kind of a trade-off always, because you have it a lot harder looking at the system than you would have it if your system runs inside the operating system.
So, more question, Aaron? No? Okay. Then, thanks very much. We now go into the coffee break.